Okay, so I guess, let me see if I can ask a question here. Okay, so let's see. I don't know what the heck just happened there, but we'll be okay. So question for you guys, and there should be a poll or something popping up pretty soon. What do you want to review? What sort of things are interesting, needed to be reviewed, et cetera, et cetera, et cetera, on there? Violet, you said rotational motion was what you guys are working on right now. Is that something you want to dive a bit deeper into? Yeah, okay. So with rotational motion, what part of that are you guys doing right now? Are you doing the torque and the Newton's laws aspect, the energy aspect, the momentum aspect, or the just basic angular acceleration, angular velocity sort of stuff? Or everything? I'm fairly open to any options here. You just did angular acceleration. Okay. So it sounds like, so you're doing questions like, we've got this wheel that's rolling and it has this given angular velocity, and at this amount of time, it's going to have this acceleration. What's its ending angular speed? Sort of stuff like that. Okay. So I guess let's work with that. So do you want to do some review, or do you want to go on to what's probably the next topic in there? So I guess, do you want to get ahead, or do you want to just recap? I think we're good. Yeah. All right. Sounds good. You're in exactly the same spot that a bunch of my students are, where it's everything's canceled and we're all up in the air and stuff like that. All right. Let me find some notes on that, so we can do some to kind of try to split the gap here. Basically, angular acceleration, angular velocity are, the way I teach my kids, that it's really the same stuff that we learn at the beginning of the year. It's still a velocity, it's still a distance, and it's still acceleration. All we're doing is, instead of talking about it being in a straight line, we're talking about it being in some sort of rotating setup. Waves and frequency. Yes, we can definitely hit waves and frequency after this part. So where the heck is my rotational stuff here? There it is, rotational motion. Okay. So let's see, sharing this without killing the stream again would be great. There, okay. So this is the notes that I typically do for rotational motion. And it does a pretty good job. Whoa, I can't do that because that'll resize everything. Okay, so basically, and again, I can skim this. Violet, if you've got questions on something I'm going through, or Star, or anybody else here, who else is here? Josh as well. If you guys have questions and want me to stop and clarify something more, just yell at me and I will stop and go over that in great detail. But the idea is, if we're talking about rotational motion or angular motion, we need to talk about the radian. And in math, this is one of the times I tell the kids that, hey, there's a reason that in math you guys talk about stuff with radians, because it lets us describe moving in a circle without having to worry about degrees and irritating stuff like that. So the radian basically is taking the radius of the circle and wrapping it around the arc. If they're equal to each other, we've got a radian. Okay. The general formula for this is S, or distance, angular distance going through there, is R times theta, the angular acceleration. These sort of equations, I'm sure you've seen a couple of them already, are useful because they relate linear motion, this S, to our angular motion. So it would be like taking a wheel and rolling it along the ground and measuring how far the wheel rolled versus the angle the wheel rolled through. This lets us relate linear motion to rotational motion in a very nice, easy way. All right, angular velocity is basically just a velocity. don't get tripped up by the symbols. It's really just talking about, hey, we are looking for a speed in here. So just like velocity is distance over time, angular velocity, omega, is angular distance. So theta, the angle in radians over time on here. And omega tends to get units of things like 1/seconds or revolutions per minute or revolutions per second. That sort of stuff like that is where we are going to be having slightly different units. But you could see this as RPM would be a really common everyday example, but also 1/seconds or radians per second for the units for angular velocity. But again, it's just a velocity. Don't get scared of it. Don't get tripped up because of it. It's just a plain, nice, angular, just a velocity. Let's leave it at just a velocity. All right, I'm going to skip this part because this is more prepping for APC, not on the AP exam there at all, or AP1 exam, but that was talking about what is positive angular velocity versus negative. Basically, short answer is if you're clockwise, you're negative. If you're counterclockwise, you're positive. So if you guys remember lefty loosey, righty tighty for loosening a bolt or something like that, if you're going to the left, we have a positive velocity that will make it rise up, and a negative velocity will be going the other way. And then last but not least, angular acceleration is just an acceleration. It's the change in velocity over time. So just like at the beginning of the year, you guys learned about linear acceleration. V equals V naught plus AT, or A equals delta V over T sort of equations. Here we've got the same deal, except for now we're just replacing symbols. Angular acceleration is the change in angular velocity over time. And it's an acceleration. It's now how much is our velocity changing in the rotating frame of reference in there. So you have angular acceleration going on. It gets this symbol alpha and stuff like that. Skip the derivation. Again, we get these couple of very neat, handy equations. This V equals R omega is the equation to remember. It's not in your reference tables, which is really unfortunate. But this is the equation going forward with rotational stuff that will be super useful, because most of the questions we're going to be seeing, talking about energy and stuff like that going forward, will involve velocities, and a linear velocity and a rotational velocity combining together. So this V equals R omega, or V equals omega R, will be super duper useful to memorize and be able to work through it. Okay. And then the last thing I would say as far as angular acceleration goes, basically we get to just rewrite all our equations. And some of these are on your reference tables. This one is, and the theta equals theta naught plus omega t one is. The last equation is not, but if you just say, oh, well, it looks like anytime I see a v in an equation, that's a velocity, I'm going to replace it with an omega. That's an angular velocity. And anytime I see an A, I'm going to replace it with an alpha, because that's an angular acceleration. And anytime I see an X, I'm going to replace it with a theta, because that's an angular distance. And that lets you generate those other ones. Pretty straightforward. All right. And then sample question with the answer already shown, because I can't click through PowerPoints on here because it's to Google. But here's a simple one where you're calculating a lot of the numbers. Some of the other things you'll do are more conceptual, but basically this one is, you've got a turntable. It has an acceleration of 12 radians per second squared. We need to start it moving at a certain speed. So it rotates through 400 radians. There's a distance in a certain amount of time. How fast do I have to have it moving at the start? So we're given a theta of 400 radians. We're given an alpha of 12 radians per second squared. We're told it's 6 seconds, and we're looking for omega. And just like you would at the beginning of the year, I've got an acceleration, a distance, a time, and I'm looking for an initial velocity. Jump over to the reference tables, find an equation that's going to work. In this case, the theta equals theta naught plus omega t, omega naught t plus 1/2 alpha, that equation right there, the distance one, lets you plug stuff in and solve for omega. And then we've got our answer right there. Right. Yeah, and I don't want to jump into the next part because that's new stuff and you want to just review. All right. Questions on angular stuff, because that was a good chunk of. All right. So Star, looks like you wanted to do waves and frequency. So let's jump into waves and frequency for a little bit, and then we will get back to whatever else. So if you guys have more questions on angular stuff, I'm going to leave it kind of on the back burner for right now, but please throw a question, comment in the chat, and I'll get back to it when we get to it. So Star, waves and frequency. Any sort of context? Is this something we are just starting off with? Is this the review? Waves, what kind of waves? That sort of stuff like that. Any advice you can give me on where we wanted to look at? Okay, so transverse waves. Okay, gotcha. All right, let's see. I know somewhere in my list of stuff, we've got some transverse wave things here. Have you guys gone into wavelength, period, that sort of stuff like that? Hey, there we go. All right, so let me start making some transverse waves here. All right, so this is PhET simulations. I will put a link to this in the slide somewhere, but if you just Google PHET, it basically takes you to this little simulation. There's ones for all sorts of stuff on here, a lot for waves on here, which is really good. So you want to talk about waves and frequency. So what's the difference? Transverse and longitudinal. Okay, so transverse, which is what I'm showing on the screen right now, we'll slow motion it. If you look at each of these green dots that are flying around here, they are only going up and down, while the entire wave is moving left to right. Okay? They are not moving the same direction as the wave. These are perpendicular. The wave is going towards the right. That means it's a transverse wave. Just if this was a longitudinal wave, they'd be going the same direction. They'd wiggle back and forth like this. Let me see if I can find an example here. Let's just see what we can find here. So video, anything good, blah, 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 blah. Looking for something nice. Okay, so sure, we'll watch this YouTube one really quickly here. Hopefully. I don't know how the sound's going to work at all, but I'm just going to kind of get through. Okay, so for a actually, I'll just mute it. Longitudinal wave, you would squish the spring and it would go through. You'd make this back and forth sort of motion in there. And you're getting this oscillation in the same direction the wave is going. A transverse wave, you'd wiggle up and down, up and down, up and down, up and down. The particles move perpendicular to the way that the wave is moving. Okay, and that's the big difference. Examples of this, longitudinal waves are sound waves. So we're going to be dealing a lot with sound waves in the waves unit that you'll eventually get to or may have already done. Those are all longitudinal waves, squishing back and forth, back and forth, back and forth. Transverse waves are light waves, waves on a slinky, water waves, stuff like that, where they vibrate up and down. Okay. Now, Star was asking about frequency. Frequency is how often that this wave repeats itself. It is the number of waves that happen in a given amount of time. Waves divided by time. And as I change this, let's go back to normal mode here. If I turn the frequency up, notice we are getting our waves happening much, much, much more frequently, hence frequency, in here. So in this case, I do have a timer. Okay. So in this case, let's just see here. 1 wave, 2 waves, 3 waves, 4 waves, 5 waves. So it took 1.68 seconds for 5 waves. So our frequency will be 5 divided by 1.68. Come on, Google, work with me here. Or roughly 3 hertz, 3 waves every second. That is frequency. 3 hertz. How about that? 3 waves every second. If I crank this frequency down, let's see, if I get it to 1 wave a second, it should take, reset. It should take 1 second for us to get 1 full wave. And there we go. Okay, so I can't click the timer very good, but we know as AP students, human reaction times are terrible. So use a better device that's not a human to time that. But that basically is the frequency, how often a wave appears. 1 hertz means 1 wave every second. 3 hertz means 3 waves every second. 0 hertz means no wave at all. Now, what does this mean for us as humans? Well, when we talk about the frequency of a wave, we hear or we see different colors or different notes depending on the frequency. So in general, I can't pull that up because that would be hearing, and I don't know if sound is going to work here. In general, we can hear the higher the frequency, the higher the pitch it sounds. So a shriek versus a real bass note, the bass note's going to have a low frequency, and the shriek or the scream is going to be much higher frequency on there. The higher the frequency, the more waves we get, the higher the pitch is to us. And if we're talking about light waves for this, the higher the frequency, the more blue or purple the light is. So for example, if I can find a book, here's a book right here. The red in this book, the red is a low frequency. The orange is a bit higher. The yellow is a bit higher than that. The blue's even higher than that. Okay? Or if you're thinking about playing a piano or something like that, low notes have a low frequency and high notes have a higher frequency. Okay? The other thing we need to look at with frequency is how it affects what the wave looks like. So we have more waves with a higher frequency. That also means that each wave takes up a shorter distance on there. Okay, so I'm going to pause it right here. This wave looks like it takes about 2 centimeters, give or take on there, with a frequency of 3. If I turn the frequency down to 1, let's see, can I get all the way down to 1? There we go. I'll let this play out for a second here. And now I want to see if I can get a whole wave in here. Okay, now looking at this, we see this wave. Wow, this wave is almost 6 centimeters longer. The wavelength, the length of the wave, changed a bit because we just stretched out that wave. The interesting part, and Star, I'm sure that you guys will talk about this soon if you haven't already, is that the product of the frequency and the wavelength, V times wave, or F times wavelength, frequency times wavelength, gives us the speed of the wave. So in this case, this wave looks like it's 6 meters per second, 6 times 1. And if I crank the frequency up to 3 again, we should get a distance of about 2 centimeters. And there we go. 3 hertz times 2 centimeters is also 6 centimeters per second. So the product of those things gives us the velocity, and changing the frequency doesn't change the velocity of the wave. All right, and we're back. All right, so looking at the not so many comments in there. All right, let's do some free response stuff. Let's jump into that. So I'm going to go find my slides again, wherever I left those last time. Here they are. And I want to present that. Okay, cool. So now, let's see. For the sake of right now, we are doing the 2016 slides, or 2016 free response questions. I just picked a few. I did not pick what I thought were the easiest ones. I did not pick what I thought were the hardest ones, but it's a good mix, and hopefully it's stuff that you guys are either going over right now or have recently gone over. So hopefully that'll work. Let's see if I can find my, okay, so you're sharing the whole thing there. I guess it'll work. Ignore the website on there. That's not important. What's important is in the box right here. We've got a free response question, hopefully. Maybe not. Hey, there's my hand. Okay. So this one is the first question in the 2016 free response section. This is basically detailing a couple different things. Have you guys done a ton of free response questions before, or is this something fairly new? All right. So as you guys know, there are 5 questions on the AP exam. Free response questions. They give you an hour and a half to do them all. And for each question, they give you a suggested amount of time. In this case, it's 13 minutes. So they're saying that a 13-minute chunk should be enough time to accomplish this question for a, I'm going to say average AP student. I don't know if average is the right word, but they're saying don't take more than 13 minutes on this question. This question is also worth a grand total of 7 points. There are 7-point questions, and then there are 12-point questions on there. The 7-point questions are typically shorter. And yeah, well, let's just dive into it here. All right, so we're going to start off by doing, come on, focus, nice camera. There we go. Doing the first part here with this. So we have a wheel with a given mass, rolling down a ramp that makes an angle to the theta. The ramp exerts a force of static friction. So we have friction going on here. So the wheel rolls down the ramp. All right. Part I, or part AI, on the diagram below. Draw and label the forces. Not the components, so just the literal forces that act on the wheel as it rolls down the ramp, which is indicated by the dashed line. Clearly indicate at which point on the wheel each force is exerted. Draw each force as a distinct arrow starting on and pointing away from the point where the force happens. Don't worry about the links. All right, so with this, how many forces are there that are acting on this wheel? There's 3. All right, I agree. There are 3 forces on here. Anyone want to take a stab at where they, or let's go through. Violet says friction. That is one of them. Okay, so we'll start there. Where is friction? And normal force. Okay, cool. And mg. Nice. Okay, so we got all 3 in the chat. Where does friction actually take place on the wheel and the ramp? Which point do we see friction acting on? Okay, the base of the wheel opposite, yes. The base of the wheel opposite the direction of motion. So we're going to have a dot be right at the bottom. Why is my video not playing nice here? This is one of those days where everything just seems to not work right. Okay, there we go. That's better. So we have force of friction going up the ramp. I'm not sure whether your teachers use a single F. I use a double F, capital F for force, lowercase f for friction on there, but that is the force we're looking at here. Okay. Other options, we've got mg. Mg always acts from the center of mass. So this one will be here, and going straight down will be mg. Again, apparently my internet is pretty terrible right now. Which I wish would be better, but we will see what happens. And then finally, you've got the normal force, which will be perpendicular to the ramp going upwards. All right, so hopefully that will click in pretty soon. There we go. Okay, so with that, we have our 3 forces on here. Normal force perpendicular to the ramp going straight up, force friction going up the ramp, and gravity going straight down. All right, double I, as the wheel rolls down the ramp, which force could cause a change in the angular velocity of the wheel with respect to the center of mass. So which of these forces could make it actually rotate differently? Well, this is where, and again, if you guys haven't done rotational motion, this one would be kind of tough. But the best answer is the only force that is actually perpendicular.